Hello and welcome to Organic Chemistry Companion. In this video, we'll be going over resonance structures and why they are so important to master when you're learning organic chemistry. So what are resonance structures? Well, these are various structures that we can draw for a molecule that help us understand how electrons are shared between the atoms in the molecule. And this can help us predict how the molecule will react and which parts of the molecule are the most reactive. It can help explain why certain reactions happen and which parts of the molecule may be nucleophilic or electrophilic. And so why do molecules have resonance structures? Well, molecules are generally more stable when they can share electrons over multiple atoms, and this helps the molecule to be lower in energy. So how do we know if a molecule has resonance structures? Well, the quickest rule of thumb that I like to use is to look at the molecule and determine if it has 3 or more sp2 or sp hybridized carbon atoms that are adjacent to each other. So if you haven't watched my hybridization video yet, make sure you check that one out so you can identify the hybridization of each carbon atom. If we take a look at this molecule here, you'll notice that these 2 carbon atoms contain the double bond, and so they're definitely sp2 hybridized. Now, what might not be obvious is that this carbon atom here is also sp2 hybridized, and the resonance structure can explain why. So when we're drawing resonance structures, we use this double-headed arrow to indicate that the structures we'll be drawing are resonance forms of the same molecule. And to start drawing a resonance structure, we want to start our arrow from either a bond or a lone pair of electrons, and we want to push them into a different part of the molecule to distribute the charge. So if we start our arrow here at this negative charge, we can draw an arrow forming a double bond between these 2 carbons, which is going to push the electrons in this double bond onto this carbon atom, like this. And so when we draw the resonance structure, we've now created a double bond in between those 2 central carbons, and that carbon on the end now has the negative charge. So these are resonance structures. And when we look at them, we might wonder, which is the true structure of this molecule? And the reality is that the true structure of the molecule is somewhere in between these 2. And the resonance structures, again, are a way for us to explain how the electrons are distributed across this molecule. So another important concept when it comes to drawing resonance structures is being able to express the bond order of each bond. And this is basically just a way to explain if the bond is a single bond or double bond or triple bond and how that's averaged out across all the resonance structures. So for example, this bond here on the right-hand side of the molecule, this bond is a single bond between these 2 carbons, and it stays that way through all the resonance structures that I've drawn, just these 2 in this case. And so we would say the bond order of this single bond is just 1 in both cases. Now, if you take a look at the double bond, you can see that it's moving between these 2 carbons on the end and the 2 in the middle. And so this double bond here, or this bond between these 2 carbons, this is going to have a bond order of 1.5. And then similarly for the bond in the middle, you can see on the structure at the left, it's a single bond, but on the structure on the right, it's a double bond. So it's going to have a bond order somewhere between single and double bond. Again, we're going to write that as 1.5. Now, if we had a double bond that didn't participate in resonance between these 2 structures, that would have a bond order of 2. Similarly, a triple bond that didn't participate in resonance, for example, that would have a bond order of 3. Okay, so let's draw the resonance structures of this methoxybenzene. So you'll see a lot of substituted benzene derivatives on homework problems and test problems, so it's really important to master resonance structures with these so that you know where they react. So to start out drawing the resonance structure, remember the oxygen atom has 2 lone pairs, and let's start by pushing one of those into this bond here. That's going to take the electrons in this double bond and push them onto this carbon. So the resonance structure is going to look like this. Remember, oxygen has 3 bonds now, so it's going to have a positive formal charge. And then to draw the next one, this pair of electrons is going to be donated to that bond, and these electrons in the double bond will go to that carbon. And then there's one more resonance structure we can draw where these electrons form a double bond there. And then that's going to push the electrons in this double bond onto this carbon. Okay, and now we've just drawn all the resonance structures of this methoxybenzene. Okay, so let's take a look at this example. And if you remember my tip that I mentioned at the beginning of the video, If you can identify 3 or more sp2 or sp carbons, you can use those atoms to start drawing your resonance structure. And so we have 2 sp2 carbons that are involved in this double bond here. We do have the oxygen with 2 lone pairs that could potentially donate electrons somewhere, but we have this carbon in the middle that is sp3 hybridized. So this is actually a trick question. So this molecule will not have any resonance structures because you can't push these electrons into this double bond across this sp3 carbon here. So there are no resonance structures for this molecule. Okay, so this is an example with a carbonyl. And so carbonyls often have resonance structures, and that can explain how they react a lot of times. So it's important to be good at drawing resonance structures with carbonyl molecules. So for this amide, remember this nitrogen has a lone pair. And to start off the resonance structure, you notice that there are 2 sp2 atoms next to it. So it's going to take those electrons and move those into the carbonyl here. That's going to push this double bond's electrons up to oxygen. And in the resonance structure for this, we're going to have nitrogen with a positive charge, oxygen with a negative charge, and that's it. So we've just drawn a resonance structure for this amide. It's okay that the resonance structure has charges like this, so they're balanced, right? A positive charge and a negative charge. This actually explains why in some cases the oxygen atom can be a nucleophile, and if you're drawing a mechanism, you might want to start with the lone pair on oxygen. So it's also possible to have resonance structures with an electron deficient molecule like this. So this is a carbocation at this benzylic carbon here. And so to draw a resonance structure for this, remember we always start our arrows on bonds or electrons. So let's start with a double bond here. We're going to move that outside the ring. That's going to result in sharing electrons with this carbon, so it's going to have a full octet. But we're going to have a carbocation inside the ring now, at that position. And similarly, we can take electrons in this bond, move them over here, so we'll have a double bond between those 2 carbons. So our positive charge is on this carbon. So this double bond in the same way can move to these 2 carbons, and that's going to open up a positive charge inside the ring at the other carbon there. Okay, so that's all the resonance structures for this positively charged benzylic cation. Again, remember, we do this the same way as when you have an anion. You always want to start your arrows, as we did here, with a bond in this case, or sometimes with electrons. But you treat these exactly the same way as you do an anion when you're drawing resonance structures. Okay, so here's an interesting example that has multiple double bonds in it with this oxygen atom. So to start drawing the resonance structures, remember the oxygen has 2 lone pairs. We can start there. Let's take these electrons and donate them into a double bond between the carbon and oxygen here. So that's going to result in moving these electrons up to a double bond with those 2 carbons. And then the carbonyl electrons in the double bond are going to move onto the carbonyl oxygen. So the resonance structure for this looks like this. Okay, and our charges balance here, we've got a positive and a negative charge, so that's a good way to check yourself as well when you're drawing resonance structures. You shouldn't ever be adding or subtracting charges between structures. You always want the total number of charges to add up to be the same number between the different resonance structures. So you can also have resonance structures with triple bonds. So here's an example of that. We have an anion next to a nitrile. So we're going to take these electrons, just like we do in every other example, and donate them into a double bond here between these 2 carbons. That's going to take these electrons in the triple bond, move them up to nitrogen. So the resonance structure for this looks like this, where we have negative charge on nitrogen now, and that's it. So we don't treat these any differently than we do the ones with double bonds, so triple bonds participate in resonance just like any other structure. So you can also have resonance structures with radicals, and if you haven't learned about radicals yet, I'll probably make a video on radicals at some point here. But essentially it's sort of in between a carbocation and an anion, in the sense that this carbon atom right here has 7 electrons, so it has a CH bond contributing 2 electrons. It's bound to 2 other carbon atoms, so in total from the bonds it has 6 electrons. Now the radical at this position is essentially an unpaired electron, and in drawing resonance structures with radicals, you basically are going to follow the same rules as you do with carbocations and with anions. And that carbon atom is going to seek to gain 8 electrons again, as it does in every case, to just try to satisfy the octet rule. So when we're drawing resonance structures with radicals, we use these single-headed arrows to represent how the electron is going to form a double bond between these two carbon atoms. And so we're going to take one electron from this double bond and use it to make a double bond between these two central carbons. Now that's going to leave us with one electron in the double bond, and it's going to be placed on this terminal carbon here. So in our resonance structure, we're going to have a double bond between those two central carbons as we've drawn, and the terminal carbon atom is now going to have the radical. So again, we use the same exact rules for drawing resonance structures with radicals. They're no different than carbanions and carbocations, but it just takes a little bit of getting used to, and again, doing several practice problems to become a master at drawing resonance structures. So let's take a look at the structure of the nitrate anion. So this is an example where you may be given this on a test or a homework problem, and you don't know the structure of the molecule, and you may have to draw the line drawing, the Lewis dot structure, and the possible resonance forms of this molecule. So if we were going to start out doing that, the first thing we want to do is calculate all the valence electrons that we'll be accounting for in the structural diagram. So nitrogen has 5 valence electrons, and we know that from looking at the periodic table. If you've seen my Lewis dot structure video, you know how to calculate that. For each oxygen atom, we're going to have 6 valence electrons, and there are 3 of them here, so that's 18 total. Now we also have a minus charge on this molecule, so that's going to add 1 electron overall. So we have 5 plus 1 plus 18. That equals 24. So to start distributing the electrons, let's just draw out nitrogen, oxygen, oxygen, oxygen. And initially you might not know that nitrogen is bound to all 3 of these oxygens, but it just takes a little bit of trial and error to keep drawing the electrons in until you get it right. So to account for all the valence electrons, we have 24 here, and remember, every atom needs to satisfy the octet rule, so each atom wants 8 total electrons. So let's start putting in the electrons that are involved in the bonds first. So we're going to have 2 electrons in a bond between these 2 atoms, nitrogen and oxygen. We're going to have 2 for that pair, and then 2 more here. Now nitrogen needs 2 more electrons to satisfy the octet rule. Let's put 2 more in, and this is going to form a double bond between the oxygen and nitrogen. Now, nitrogen has 8 total electrons, so we can't put any more into double bonds here or here. So let's fill in the remaining electrons on the oxygen atoms around the molecule. So this oxygen atom needs 6 more to complete its octet. Remember, it's sharing these 2 with the nitrogen atom. This oxygen needs 4 more since it's sharing 4 electrons in a double bond with nitrogen. And then this oxygen needs 6 more since it only has 2 in its bond with nitrogen. And so if we count up all the electrons, we have 8 here, right here, we have 8 here, and we have 8 here. So we've used all 24 electrons, and each atom has a complete octet. Now when we draw the line structure for this molecule, we'll be able to recognize the formal charges. So this is the line structure, and remember, nitrogen with 4 bonds is going to have a formal charge of +1. Each oxygen atom is going to have a -1 charge because it only has 1 bond and it has 6 total electrons in addition to that. And the total charges of this molecule add up to -1, which is the charge on the nitrate anion, so our charges match what was given to us here. And now at this point, we can draw any possible resonance structures. So when we draw the resonance structures here, we can start with the electrons on this oxygen, and we're going to use those to make a double bond between the oxygen and nitrogen. Now that is going to give nitrogen more than 8 electrons unless we take electrons from this double bond and move them up to oxygen. So that's what we're going to do. And then the resonance structure is going to look like this. So overall charges balance, again, we have a -1 net charge, but we've essentially moved a negative charge from this oxygen up to this one by moving the electrons. So that's one of the possible resonance structures. And now we can also take electrons from this oxygen. Let's just use that charge to indicate that. We're going to move those electrons into a double bond between nitrogen and oxygen, and then move these electrons up onto oxygen. Okay, so in all 3 of these structures, you'll notice that nitrogen still has a positive charge, We're essentially just shuffling electrons between the oxygen atoms in this molecule. But this is the correct way to draw the 3 different resonance forms of the nitrate anion. So as I mentioned, it takes a lot of practice to be able to draw and recognize resonance structures. Once you do a lot of practice problems, you'll be able to recognize them very easily, and this will help you out quite a bit as you're drawing mechanisms for reactions and learning more as you go on in organic chemistry. So if you found this video helpful, please give it a like. That really helps my channel reach as many people as possible. Subscribe if you'd like to see some more helpful chemistry tutorials, and comment below if there are concepts or practice problems that you'd like to see me cover. I also do one-on-one and group tutoring, so send me an email at organicchemistrycompanion@gmail.com if you'd like to get in touch. Thanks for watching.